Okay, so for today, let's say that we have a projectile that's being launched from some cannon. And when the cannon is sitting still on the ground and it launches at some angle, well, we'll determine in a sec, at some speed v naught, its maximum range, the maximum distance that it can fire this cannonball, is L. Now we already know what the maximum range corresponds to for angle. It means that this launch angle is going to have to be a 45-degree angle. But if we didn't remember that, we have derived this several times before. The overall range for any projectile is going to be, well, maybe I should write it out this way. In this initial case where the platform is not moving, the range is obviously going to be a v naught squared sine 2 theta over g. That's a pretty standard thing that we've worked out before. And if I'm trying to talk about a maximum range, then sine 2 theta has to equal 1, which means theta is 45 degrees. Okay, so we know that. But now we're going to mix things up a little bit. What we're going to do is say, now imagine that same cannon is placed on a platform that can move. And let's say that this platform is moved forward to the right at the same speed that the cannonball gets launched from the cannon. So that v naught here is the same as the v naught that comes out of the cannon. And our new question is, what's the maximal range? Just given some moving platform here with respect to the ground, what is the maximal range of this projectile? Notice, because the platform itself is moving, I can't immediately say that this angle, which I'm now calling phi, has to be a 45-degree angle. In fact, it could be something else. We're going to have to maximize something. So what we'll do here is we'll look at this situation from the ground frame. So there'll just be an initial component to the initial velocity, an extra component to the initial velocity of our launched cannonball here. So let's return to our kinematics equations. I'll get those up on the board. Okay, so what do we got? Obviously, this thing, this projectile is only accelerating downwards due to the influence of gravity. It doesn't really matter whether the platform itself is accelerating or not, because I'm going to assume that at least at the time this is launched, it is moving to the right at v naught, and what it does afterwards is irrelevant for the cannonball. We're assuming the cannon is launched instantaneously. So this x is going to be, hopefully, eventually r, the range of this projectile. We're going to start our coordinates and our clocks and everything right at t equals 0. So I'll go ahead and put a little, this is a y direction and this is an x direction. And it starts at x naught and y naught both equal 0. This piece is what's a little different than normal. Because yes, we are going to have a v naught cosine phi piece from the velocity of the cannonball relative to the platform, but relative to the ground, I also have this extra piece, which is another v naught in the positive x direction to account for the platform moving. So this is the relative x velocity for the cannonball to the ground. There's an extra piece here. And there's no acceleration in the x direction. In the y direction, it's going to start and end at the ground. That's kind of what we're interested in. So both of those terms are 0. My y component of the velocity only has the upwards component because the platform is not moving in an upwards direction at all. So that's as normal. And then, as usual, the acceleration is negative g. Okay, so we can easily solve this bottom equation for time. Notice t equals 0 is a solution, but it's kind of a trivial, unimportant one. And I'll then plug that time back in here to get r as a function of phi. So what are we going to have? I'll go ahead and pull out a v naught from here. And then for our t, well, like I said, we'll cancel out one of these t's, and then there's not even a quadratic to solve. I'll end up with a 2 v naught sine theta over g. We've seen that. That's just the total flight time. So the only thing that's extra is this little plus 1. Now, I want to maximize this range. That means I'm going to have to take a derivative and set it to 0, so we'll do some calculus. Maybe before that, I will actually, I will actually rewrite this a little bit. Let's see what we have. So first off, we've got a 2v0 squared over g. And I'm sorry, that should be a phi, not a theta there. And before we get to the calculus, let's remember that in this problem, we're actually not supposed to be given v0. We were given L, which is the maximal range according to the projectile fired normally. And from this result that we said here, we actually have that L is v0 squared over g. So actually, v0 squared over g, I can just replace with the letter L right now. Okay, now let's maximize. So I'll take the derivative with respect to phi. Thing out front is a constant. But I do have a product rule, so let's be real careful about it. The derivative of cosine is, of course, negative sine. The 1 doesn't contribute to the derivative. And then I'll have my 1 plus cosine. The derivative of sine is regular cosine. And a little simplification can happen here. Let's actually try to write everything in terms of cosine, because I see that I'm going to have a linear term in cosine here. So I'm probably going to need like some quadratic to factor in cosine. And I'm wanting to set this whole thing equal to 0, of course, because we're trying to maximize. So 2L, I can divide that out. And I'll just have 0. Negative sine squared. Let's use a Pythagorean identity here. Sine squared plus cosine squared is 1. So we know that this negative sine squared is going to be what? 1... or it's cosine squared minus 1. And then here I have a cosine squared again, and I've got an extra cosine. All right, so that looks a little messy, but it's not so bad. There's a 2 cosine squared plus cosine minus 1, and that factors. So let's see, that'll be what? 2 cosine minus 1 times cosine plus 1. Double check, so I get the 2. I'll have a plus 1, plus 2 cosine and a minus 1 cosine and then a minus 1. So that factors nicely. Okay, so use our zero product property. We know that one of these has to be 0. If this term is 0, cosine phi would have to equal minus 1, which means phi would have to be pi. In other words, you'd be firing it directly backwards. And I think even just basic physical intuition tells you that's probably a way to minimize your total range, not maximize it. So it does give us an extremum. The derivative is 0 there, but it's a minimum. So we're not interested in that. What I am interested in is this term being a 0, which means that cosine phi is a half, or phi, it looks like a D. Let's make that a proper phi. A phi of 60 degrees would be the launch angle. If I want to take that now and plug it back into my R, maybe I'll call it R star or something for maximum. Maybe I'll call this phi star for maximum phi. What's the easiest one? Probably this one right here. So we'll have a 2L. Sine of 60 degrees is root 3 over 2. And then we have a 1 plus the cosine of 60 degrees, but that, of course, is just a half. And what do we end up with? Those 2's will cancel. That's 3 halves. So I'll end up with 3 root 3 over 2L as my final answer. So let's just review what we've done here. We said that if you have a cannon that's launching a maximal distance of L, and then you put it on a platform that moves at the same speed as the cannonball launch speed, then the max distance that you can reach is larger than L, obviously. 3 root 3 over 2. 3 root 3 over 2 numerically is about 2.6. And okay, so you'll get about 2.5 times as much distance on this moving platform. Okay, so just keep in mind that when you're dealing with moving platforms, you really got to include this relative motion into your kinematics equations, but otherwise, not much has changed. QED.